41,000 years ago, Earth's magnetic field collapsed to 6% of its current strength. The auroras shifted from the poles toward the equator. The magnetosphere, the planet's shield, contracted so severely that the flux of cosmic rays bombarding the surface doubled. This is not a myth, not a hypothesis, not an exaggeration. It is measurable, precisely reconstructed physics, and it is far more dramatic than any version that ever made it into a headline. Before we go any further, please subscribe to this channel. Your support genuinely helps us keep making films like this one. Thank you. Now, let's start with what Earth's magnetic field actually is, and what it means for that field to briefly, dramatically fail. Earth's magnetic field is generated deep within the planet, in the outer core, a layer of molten iron and nickel roughly 2,200 kilometers thick, surrounding a solid inner core and sitting nearly 3,000 kilometers beneath our feet. As this liquid metal churns, driven by heat escaping from the planet's interior and by the Coriolis effect produced by Earth's rotation, it generates electrical currents, and those currents generate a magnetic field. In a self-sustaining process, geophysicists call the geodynamo. This field extends far beyond the planet's surface, forming an invisible protective structure called the magnetosphere, which deflects the majority of the charged particles streaming outward from the Sun and shields the atmosphere from cosmic radiation arriving from deep space. It is worth pausing on the specific physics of the geodynamo in more detail, because the mechanism generating Earth's magnetic field is genuinely intricate, and understanding it properly makes clear why a temporary collapse like the Laschamps excursion is physically possible at all, rather than a fixed, permanent feature of the planet. Earth's outer core consists of liquid iron and nickel, maintained in a molten state by pressure and temperature conditions reaching roughly 4,000 degrees Celsius, hot enough to melt these metals despite the crushing pressure of the overlying mantle and crust. This liquid metal is not still. It churns in a continuous, turbulent motion driven by two separate physical processes operating together. The first is thermal convection, heat escaping from the solid inner core, itself slowly crystallizing and releasing latent heat as it grows, along with heat generated by the ongoing decay of radioactive elements distributed throughout the core, causes hotter, less dense liquid metal near the inner core boundary to rise, while cooler, denser liquid metal near the mantle boundary sinks, establishing large-scale convective circulation patterns analogous to the convection currents visible in a pot of boiling water, though operating on a scale of thousands of kilometers rather than centimeters. The second process is the Coriolis effect, produced by Earth's own rotation. Because the planet spins on its axis once every 24 hours, any fluid moving within it experiences a deflecting force that curves its path of motion. In the same basic way, Earth's rotation curves the path of large-scale atmospheric and oceanic currents at the surface. Applied to the convecting liquid metal of the outer core, this Coriolis deflection organizes what would otherwise be relatively simple, chaotic convective churning into large, organized, twisting columns of flow, roughly aligned with Earth's rotational axis. These twisting helical flow patterns are essential to the dynamo process, because a simple, straight flow of conducting metal cannot sustain a magnetic field on its own. The specific twisting geometry imposed by rotation is what allows the system to convert kinetic energy from the churning metal into a self-sustaining magnetic field through electromagnetic induction. In a feedback loop, where the existing magnetic field induces electrical currents in the moving conductive fluid, and those currents in turn generate additional magnetic field, reinforcing the original field rather than dissipating it, provided the flow pattern and conductivity remain within the right physical parameters for the process to remain self-sustaining rather than decaying away. This entire system, while remarkably stable across most of Earth's history, is not perfectly, permanently stable, because the underlying flow patterns within the outer core are not perfectly steady either. Convective flow within a turbulent fluid system, this large and this energetic, naturally develops instabilities and fluctuations over time, and computer simulations of the geodynamo process, run by geophysicists attempting to reproduce Earth's actual magnetic behavior using the known physical properties of the outer core, have demonstrated that these models naturally, spontaneously produce occasional excursions and full reversals as an inherent expected feature of the underlying physics, rather than requiring any unusual external trigger. In other words, events like the Laschamps excursion are not evidence that something went wrong with Earth's magnetic field. They are evidence that the field is operating exactly the way the underlying physics predicts it should, given enough time. A genuinely chaotic system that, left running long enough, will periodically pass through episodes of instability as an ordinary, expected part of its own internal dynamics. Under ordinary conditions, this field behaves with remarkable stability on any timescale relevant to a single human life. But over geological time, it is anything but constant. Roughly every few 100,000 years, on an interval with no fixed, predictable rhythm, Earth's magnetic field fully reverses. North becomes south, south becomes north, in a process that unfolds gradually, typically over several thousand years. The most recent full reversal, known as the Brunhes-Matuyama reversal, occurred approximately 780,000 years ago. But full reversals are not the only way this field misbehaves. Geophysicists have also identified a category of shorter, less complete disturbances called geomagnetic excursions, episodes in which the field weakens dramatically and the magnetic poles wander far from their usual positions, sometimes approaching or even briefly crossing the equator, before the field recovers and the poles return to something resembling their original configuration, without ever completing a full, lasting reversal. It is worth returning to full geomagnetic reversals, briefly mentioned earlier in this film, and examining the Brunhes-Matuyama reversal specifically in somewhat greater detail, because understanding how a full reversal differs physically from an excursion like Laschamps helps clarify exactly what did and did not happen 41,000 years ago. The Brunhes-Matuyama reversal, Earth's most recent full polarity reversal, is named for the two French and Japanese geophysicists, Bernard Brunhes and Motonori Matuyama, whose independent early 20th century research first identified reversed magnetic polarity preserved in ancient volcanic rock. Work that eventually contributed to the broader recognition that Earth's field has flipped polarity repeatedly across geological time. Occurring approximately 780,000 years ago, this reversal marks the boundary between the Matuyama Chron, an extended period of reversed polarity preceding it, and the Brunhes Chron, the current period of normal polarity that has persisted ever since, encompassing the entire span of documented human evolutionary and cultural history from Homo erectus through the present day. Unlike the Laschamps excursion, during which the field weakened dramatically, wandered, and then recovered back to its original polarity orientation, a full reversal, like Brunhes Matuyama, involves the field completing an entire polarity flip and then stabilizing in that new, opposite orientation for an extended period afterward, rather than snapping back to its prior configuration. Current research places the duration of the Brunhes-Matuyama transition itself, the period during which the field was actively flipping from one stable polarity to the other, at somewhere between several hundred and around several thousand years, depending on the specific methodology and rock record used for the estimate. A duration broadly comparable to, though somewhat longer than, the roughly 2,000-year full-span researchers have now documented for the Laschamps excursion. This comparison highlights an important and somewhat counterintuitive point about the underlying physics separating an excursion from a full reversal. The two phenomena appear to begin in a broadly similar way, with weakening field strength, increasingly complex multipolar structure, and wandering magnetic poles. And current research has not identified any clear, reliable early indicator capable of confidently predicting, while an event is still unfolding, whether it will ultimately resolve as a comparatively brief excursion that snaps back to its original orientation, as Laschamps did, or continue onward into a full, lasting reversal, as Brunhes Matuyama eventually did 780,000 years earlier. This genuine scientific uncertainty is itself part of why Chris Finlay's team, in assessing the modern South Atlantic Anomaly, was careful to describe its structural features as necessary rather than sufficient conditions for a future event. Because even Earth's own deep geomagnetic history does not provide a clean, reliable rule for distinguishing, in real time, between these two genuinely different possible outcomes, once a field disturbance of this kind has actually begun. The broader pattern connecting excursions and full reversals current geodynamo research increasingly suggests may represent points along a single underlying continuum of dynamo instability, rather than two entirely separate categories of physical process. Whether a given instability episode ultimately resolves as a brief, recovering excursion or escalates into a full, lasting reversal may depend on subtle, currently poorly understood details of the specific flow instabilities developing within the outer core at that particular moment, precisely the kind of detailed internal physics that remains among the most actively studied and most genuinely unresolved frontiers in the broader science of Earth's magnetic field. It is worth pausing on a planetary comparison that throws Earth's situation during the Laschamps excursion into sharper relief. Mars, a planet that experienced something considerably more severe than a temporary excursion and never recovered. Mars almost certainly possessed a genuine, Earth-like internal dynamo and a correspondingly strong global magnetic field early in its history, roughly 4 billion years ago, generated by the same basic physical process of convecting. Electrically conductive fluid churning within its metallic core. Evidence for this ancient field survives today in the form of strong, patchy magnetization preserved within some of the oldest rock formations on the Martian surface, particularly across the southern highlands. A permanent paleomagnetic record functionally similar to the volcanic rock evidence that first revealed the Laschamps excursion here on Earth, except considerably older and considerably more consequential in its ultimate outcome. At some point within roughly the first 500 million to 1 billion years of the planet's history, Mars's internal dynamo shut down entirely, most likely because the planet, being considerably smaller than Earth and therefore losing its internal heat more rapidly, cooled to the point where its core could no longer sustain the vigorous convective churning a working dynamo requires. Unlike Earth's outer core, which remains hot and actively convecting today, Mars's core appears to have cooled enough relatively early in the planet's history that whatever dynamo process once operated there simply stopped permanently, rather than merely weakening temporarily as Earth's field did during Laschamps. The consequences of this permanent shutdown, reconstructed through decades of orbital and surface spacecraft observation, illustrate directly what a truly complete and lasting loss of planetary magnetic shielding actually means over geological time, in a way that usefully clarifies why Earth's temporary, several hundred-year excursion, however dramatic, never came close to producing comparably severe long-term consequences. Without a global magnetic field to deflect the solar wind, the continuous outward stream of charged particles the Sun emits in all directions, Mars's atmosphere has been gradually stripped away directly by this unshielded particle bombardment across billions of years, a process NASA's MAVEN spacecraft, orbiting Mars since 2014 specifically to study this ongoing atmospheric loss, continues to measure directly today, detecting atmospheric particles actively escaping into space in real time. Current estimates suggest Mars has lost the substantial majority of its original atmosphere through this mechanism, transforming a planet that may once have supported a warmer climate and standing surface water into the thin atmosphered, radiation-exposed desert world observed today. The comparison matters directly for understanding the Laschamps excursion's true significance. Earth's outer core, unlike Mars's now solid core, remains hot, large, and vigorously convecting, meaning the geodynamo process that briefly destabilized during Laschamps was never in any genuine danger of shutting down permanently the way Mars's dynamo eventually did. The underlying engine generating Earth's field remained fully intact and operational throughout the entire event, merely passing through a temporary period of structural instability before reorganizing back into its normal, stable dipole configuration. This is precisely why Earth's field recovered within a geologically brief 2,000-year window, while Mars's field never recovered at all across the following several billion years. The Laschamps excursion, dramatic as it genuinely was, represents a temporary stumble in an otherwise robust, long-term stable planetary system. Not any kind of genuine threat to the geodynamo's fundamental long-term viability. A reassuring distinction that Mars's considerably more severe planetary fate helps bring into proper comparative focus. The best documented of these excursions, and the one this film is built around, is known as the Laschamps excursion, named for the volcanic region in the Auvergne in central France, where it was first identified. The discovery traces back to the late 1960s, when French geophysicists Norbert Bonhomet and Jacques Babkin, studying the magnetic orientation preserved in volcanic lava flows near the village of Laschamps, found something that should not have been possible under the conventional understanding of Earth's magnetic history at the time. When lava cools and solidifies, tiny magnetic mineral grains within the rock lock into alignment with whatever direction Earth's magnetic field happened to be pointing at that exact moment, preserving a permanent, physical record of the planet's magnetic orientation, frozen at the instant of the rock's formation. The lava flows at Laschamps preserved a magnetic direction pointing in nearly the opposite direction from the modern field, a reversed polarity signature in rocks that were clearly far too young to belong to the last full reversal, which even by 1960s dating methods was already known to have occurred hundreds of thousands of years earlier. This was, at the time, a genuinely puzzling anomaly. Subsequent research across the following decades gradually built a broader picture, identifying comparable reversed polarity signatures preserved in sediment cores and volcanic deposits at sites scattered across the globe. Evidence that this was not a strange local quirk of one small region in France, but a genuine, brief, global event in Earth's magnetic history, now understood to have occurred approximately 41,000 years ago, during the depths of the last glacial period. It is worth situating the Laschamps excursion within the broader history of paleomagnetism as a scientific discipline, and within the broader catalogue of comparable events researchers have since identified, because Laschamps is genuinely well documented, but far from unique. Paleomagnetism as a field of study developed gradually across the middle decades of the 20th century, as researchers increasingly recognized that certain minerals, particularly iron oxide minerals like magnetite, present in small quantities within many types of rock, behave as tiny, permanent recorders of Earth's magnetic field at the moment those minerals crystallize or settle into place. In volcanic rock, this recording happens as lava cools below a specific temperature called the Curie point, at which magnetic minerals within the cooling rock lock into alignment with the ambient magnetic field and retain that alignment permanently afterward, essentially unaffected by any later, weaker external field. In sedimentary rock, a comparable but generally less precise recording process occurs as magnetic mineral grains settling through water gradually orient themselves with the ambient field, before becoming locked in place by ongoing sediment accumulation and compaction. Together, these two recording mechanisms have allowed researchers to reconstruct a remarkably detailed history of Earth's magnetic field extending back hundreds of millions of years, by systematically sampling rock of known age from sites scattered across the globe and comparing the magnetic orientation preserved within each sample. This broader body of work has identified numerous geomagnetic excursions beyond Laschamps, each documented with varying degrees of confidence and precision, depending on the quality and geographic distribution of the available rock and sediment record. The Mono Lake excursion, dated to approximately 34,500 years ago, occurred a relatively short span after Laschamps, and is documented primarily through sediment cores recovered from Mono Lake in California, along with corroborating evidence from additional sites since identified elsewhere. The Blake excursion, considerably older at roughly 120,000 years ago, is documented primarily through deep-sea sediment cores. The Norwegian Greenland Sea excursion, dated to approximately 60,000 years ago, adds a further data point to this broader catalogue. Each of these events shares the same basic character already established for Laschamps: a temporary, dramatic weakening of field intensity, accompanied by significant wandering of the magnetic poles away from their normal positions, without a full, lasting reversal ever being completed. The existence of this broader catalogue matters for properly contextualizing Laschamps within Earth's magnetic history. It was not a singular, one-time anomaly. It was one instance of a recurring, if irregularly timed, category of behavior. The geodynamo appears to exhibit periodically across geological time, a pattern current research suggests may occur on average every few tens of thousands of years, though with no fixed, predictable interval, making genuinely precise forecasting of the next such event, if and when one occurs, extremely difficult using currently available methods. This irregular recurrence pattern is itself an active area of ongoing research. With a September 2024 study published in the journal Geology, specifically examining peat deposits to identify additional, potentially less severe geomagnetic excursions occurring within just the past 10,000 years. Evidence suggesting that even comparatively minor magnetic disturbances, well short of Laschamps scale severity, may be considerably more common throughout Earth's recent magnetic history than researchers had previously recognized, simply because smaller disturbances leave a fainter, more easily overlooked signature in the rock and sediment record, compared to a dramatic event like Laschamps. For decades following its initial identification, the Laschamps excursion remained a subject of specialist interest within paleomagnetism, a genuinely fascinating but relatively obscure corner of Earth science, attracting serious scholarly attention but little of the broader public fascination that dramatic geological events sometimes generate. That changed abruptly in February of 2021. A research team led by Alan Cooper and Chris Turney published a paper in the journal Science that transformed the Laschamps excursion from a specialist curiosity into a global media phenomenon almost overnight. Drawing on a newly analyzed record from an ancient kauri tree in New Zealand, a tree that had lived and died precisely during the excursion, its growth rings preserving a detailed year-by-year chemical record of atmospheric conditions across that exact window of time. The team constructed what they described as the most precise timeline yet available for the excursion's environmental consequences, and their conclusions were genuinely dramatic. The researchers proposed that the sharp increase in cosmic radiation reaching Earth's surface during the excursion's magnetic minimum triggered a cascade of environmental effects severe enough to warrant its own name. They called it the Adams Event, an affectionate reference to Douglas Adams's science fiction series and its recurring joke about the number 42, since their reconstructed timeline placed the most severe effects at approximately 42,000 years ago. The specific piece of physical evidence at the center of the 2021 Cooper and Turney paper deserves closer examination in its own right, because the Kauri Tree record they analyzed represents a genuinely remarkable natural archive, regardless of how the broader causal claims built upon it eventually fared under scrutiny. Kauri trees, native to New Zealand, are among the longest-lived and largest tree species on Earth, capable of living for well over 1,000 years and reaching enormous size, with trunk diameters sometimes exceeding several meters. Critically for this specific research, Kauri wood is also remarkably resistant to decay, meaning that trees which fell and became buried in waterlogged, oxygen-poor sediment thousands of years ago can survive in a preserved subfossil state for tens of thousands of years afterward, their wood still solid enough to extract and analyze in detail. New Zealand's swampy lowland regions have yielded numerous such buried Kauri specimens, recovered periodically by excavation and prized both for scientific research and, in some cases, for their timber value once extracted and dried. The specific specimen at the center of the 2021 study had lived for a documented span of approximately 1,700 years. Its growth entirely contained within the window immediately surrounding the Laschamps excursion, meaning its annual growth rings preserved a continuous, year-by-year record spanning the excursion's most dynamically changing period. Trees form a new growth ring each year, and the width, density, and chemical composition of each ring reflects the specific environmental conditions the tree experienced during that particular year's growing season. Critically for this research, atmospheric radiocarbon, carbon-14, produced when cosmic rays interact with nitrogen atoms in the upper atmosphere, becomes incorporated into a tree's growth rings through ordinary photosynthesis, meaning that a tree's rings preserve a direct, annually resolved record of atmospheric radiocarbon concentration during each year of its life. Because radiocarbon production increases when Earth's magnetic shielding weakens and more cosmic radiation reaches the upper atmosphere, this Kauri specimen's growth rings functioned as an extraordinarily precise, natural recording instrument for exactly the kind of cosmic ray variation this film will examine shortly in the context of a separate, independent dating method, beryllium-10. The research team's analysis of this specimen allowed them to construct a genuinely high-resolution timeline of radiocarbon variation across the excursion, considerably more precise, at least for this specific narrow window, than most other available paleomagnetic archives could provide, since most rock and sediment records simply cannot be dated with year-by-year precision the way an unbroken sequence of tree rings can. This technical achievement was genuine and valuable, and it remains a cited, respected contribution to the broader paleomagnetic record, independent of the more speculative causal claims the same paper built on top of it. The Kauri tree record is, in other words. A case where the underlying physical evidence and analytical technique were sound and important, even as the broader interpretive narrative constructed around that evidence, the Adams event and its proposed links to Neanderthal extinction and megafauna decline, did not hold up equally well once independently examined. The specific claims advanced in this paper were sweeping. Cooper and Turney's team proposed that intensified cosmic ray bombardment during the magnetic minimum could have driven significant ozone layer depletion, allowing substantially increased ultraviolet radiation to reach Earth's surface. They proposed this environmental stress could plausibly have contributed to the disappearance of Neanderthals from the European landscape, a population already under separate pressure from competition with recently arrived anatomically modern humans. They further proposed the same environmental pressure might explain a documented uptick in cave art production and ochre use among Upper Paleolithic humans during this same general period, framing red ochre pigment, sometimes used as body decoration, as a plausible early form of sun protection against intensified ultraviolet exposure. They even suggested the same window of severe atmospheric disturbance might have contributed to a wave of megafauna extinctions occurring across multiple continents during roughly the same broad era. The specific atmospheric mechanism Cooper and Turney's team proposed to connect magnetic field weakening to ozone depletion deserves closer technical examination, both because the underlying physics is genuinely interesting and because understanding the specific proposed mechanism clarifies exactly what later research was, and was not, able to confirm. The proposed mechanism ran as follows. With Earth's magnetic shielding dramatically weakened, a substantially increased flux of high-energy cosmic ray particles and solar energetic particles would reach the upper atmosphere largely unimpeded. Upon striking atmospheric molecules, these energetic particles can trigger a cascade of chemical reactions, producing reactive nitrogen and hydrogen compounds, some of which are known through entirely separate and well-established atmospheric chemistry research conducted in other contexts. To catalytically destroy ozone molecules in the stratosphere, breaking down the protective ozone layer that normally absorbs the majority of the sun's harmful ultraviolet radiation before it can reach the planet's surface. Cooper and Turney's team proposed that this specific chemical pathway, driven by the dramatically increased particle flux accompanying the magnetic minimum, could have produced meaningful, sustained ozone depletion across the excursion's most severe phase, allowing significantly elevated ultraviolet radiation to reach Earth's surface for a period of years to decades. This proposed mechanism was not invented from nothing. The underlying atmospheric chemistry connecting energetic particle bombardment to ozone depletion is genuinely established science, documented in other contexts, including studies of how large solar particle events affect stratospheric chemistry on considerably shorter timescales. The genuine scientific question, never whether this chemical pathway exists in principle, but whether the specific magnitude and duration of particle flux increase documented during the Laschamps excursion was sufficient to produce ozone depletion severe enough and sustained enough to plausibly drive the specific biological and cultural consequences the paper went on to propose. This is precisely the point at which subsequent research, including the more detailed physical reconstructions this film will examine shortly, struggled to fully substantiate the original paper's more dramatic framing. While increased particle flux during the excursion's minimum is well established through multiple independent lines of evidence, translating that increased flux into a specific quantified estimate of ozone depletion severity, and from there into a specific quantified estimate of increased surface ultraviolet exposure, sufficient to meaningfully affect Neanderthal health or cave-dwelling human behavior, requires a chain of additional atmospheric modeling that the original 2021 paper did not fully work through with the same rigor later researchers would apply to the magnetospheric and auroral dimensions of the event. The physical possibility of some degree of ozone depletion during the excursion remains a reasonable, still studied hypothesis. The specific, dramatic biological consequences the original paper proposed, flowing from that depletion, represent a considerably longer, more speculative causal chain than the paper's confident framing initially suggested to the public. The media response was immediate and enormous. Headlines across dozens of outlets worldwide described a planet-altering catastrophe, an ancient near-apocalypse, explaining the disappearance of an entire human species, framed with the kind of narrative clarity and dramatic specificity that makes for genuinely compelling popular science coverage. The Adams event, as a piece of science communication, succeeded spectacularly at capturing public attention. Whether it succeeded equally well as a piece of rigorous, defensible science was a separate question, and one that the broader research community began examining closely almost immediately. The core problem, as subsequent researchers would demonstrate in considerable detail, was chronological. Andrea Picin, an archaeologist affiliated with the Max Planck Institute, and John Hawks, a paleoanthropologist at the University of Wisconsin, were among the researchers who published formal, direct rebuttals of the specific causal claims linking the Laschamps excursion to Neanderthal disappearance. Their core argument rested on a straightforward examination of the actual archaeological and genetic timeline already established for Neanderthal population decline across Europe, a timeline built independently of any magnetic field data, drawn from radiocarbon dating of Neanderthal remains and associated archaeological material at sites across the continent. That independently established timeline showed something the Adams event narrative had not adequately accounted for. Neanderthal populations across most of Europe had already been declining, and in many regions had already substantially disappeared, well before the Laschamps magnetic minimum actually occurred. The most recent, confidently dated Neanderthal remains in several well-studied regions cluster in a period predating the excursion's peak intensity by several thousand years, a gap that becomes considerably more difficult to reconcile with a direct causal relationship once the specific dates are laid out side by side rather than treated as broadly, loosely contemporaneous. A species already in substantial, well-documented decline for reasons connected to competition, climate, and demographic pressures already operating independently, cannot easily be said to have been finished off by an environmental event that arrived, in large part, after the process was already well underway in the regions where the evidence is clearest. A similar chronological problem complicated the paper's claims about megafauna extinction. The specific extinction events Cooper and Turney's paper cited as potentially connected to the Adams event span, when examined individually and carefully, a considerably broader and more staggered timeframe than a single environmental trigger, occurring in a narrow window around 41,000 years ago, could plausibly explain. Different species, on different continents, disappeared at meaningfully different times across a span of many thousands of years, a pattern generally better explained by the combination of factors this same broader body of research has already documented elsewhere. Climate shifts, habitat change, and as an entirely separate strand of paleontological research has extensively established, human hunting pressure arriving at different times in different regions, rather than a single, sudden, globally synchronized environmental shock. The rebuttal did not dispute that the Laschamp excursion itself was real, dramatic, and worth studying closely. The underlying paleomagnetic and cosmogenic radionuclide evidence for a severe, genuine weakening of Earth's magnetic field 41,000 years ago was never seriously in question. What the critique specifically challenged was the far more speculative causal chain built on top of that solid physical foundation. The leap from the magnetic field weakened dramatically to, and this specifically explains several major, independently documented biological and cultural phenomena that do not, on close chronological inspection, actually line up cleanly with the timing of the magnetic event itself. This is, in a sense, precisely the pattern this film has traced in other contexts. A genuinely dramatic, well-documented physical event, real and worth taking seriously on its own terms, becoming attached to a considerably more speculative and more attention-grabbing causal narrative that ultimately did not survive close chronological scrutiny once independent researchers examined the underlying dates carefully. Having established what the Laschamp excursion did not reliably cause, it is worth turning to what researchers have, through more recent and considerably more carefully constrained work, established it actually did involve. A picture that has become substantially more precise over the several years following the initial 2021 controversy. Sanja Panovska, a geophysicist at the German Research Center for Geosciences in Potsdam, presented a detailed reconstruction of the excursion's specific timeline and intensity at the European Geosciences Union General Assembly in 2024. Combining direct paleomagnetic field measurements preserved in rock and sediment with an independent line of evidence. Cosmogenic radionuclides, specifically beryllium-10, a rare isotope produced when cosmic rays strike atoms in Earth's upper atmosphere. Because Earth's magnetic field normally deflects a significant portion of incoming cosmic radiation before it can reach the atmosphere, periods of weakened magnetic field intensity correspond directly to periods of increased beryllium-10 production, providing a chemical proxy for magnetic field strength entirely independent of and capable of cross-checking against the direct paleomagnetic measurements preserved in rock. The beryllium-10 methodology underlying much of the precise dating work this film has already discussed, deserves closer technical explanation, because understanding exactly how this cosmogenic radionuclide dating actually works clarifies why researchers place such confidence in it as an independent check against the direct paleomagnetic rock record. Beryllium-10 forms when high-energy cosmic ray particles arriving from deep space collide with oxygen and nitrogen atoms in Earth's upper atmosphere, triggering a nuclear reaction called spallation, in which the incoming cosmic ray particle fragments the target atomic nucleus, producing a shower of lighter secondary particles and atomic fragments, including, among various other products, beryllium-10 atoms. This freshly produced beryllium-10 gradually attaches to atmospheric aerosol particles and is eventually deposited onto Earth's surface through ordinary precipitation, becoming incorporated into accumulating layers of polar ice, deep ocean sediment, and other environments where it can remain locked in place and undisturbed for tens of thousands of years afterward, preserving a chronological record of its original atmospheric production rate at the specific time each layer was deposited. Because beryllium-10 production depends directly on how many cosmic ray particles actually reach the upper atmosphere in the first place, and because Earth's magnetic field is the primary factor determining what fraction of incoming cosmic radiation gets deflected away before it can reach the atmosphere at all, beryllium-10 concentration preserved in a dated ice core or sediment layer functions as a genuinely independent proxy for magnetic field strength at the time that layer formed. Independent in the specific sense that it relies on an entirely different physical process and an entirely different category of preserved physical evidence than the direct paleomagnetic measurements taken from volcanic rock or sediment magnetic orientation. When two genuinely independent lines of evidence, relying on different underlying physics and preserved in different physical materials, converge on the same basic conclusion. In this case, a dramatic, sustained weakening of Earth's magnetic field during a specific, well-defined window 41,000 years ago. Researchers can place considerably greater confidence in that shared conclusion than either line of evidence could support entirely on its own. This is precisely the kind of methodological cross-validation that separates the specific, well-supported physical claims this film has traced from the more speculative causal claims the original 2021 paper built on top of them. The magnetic field weakening itself rests on this kind of genuinely convergent, mutually reinforcing evidence from multiple independent physical processes and preserved in multiple independent geological archives scattered across the globe. The specific claims about Neanderthal extinction, ochre use, and megafauna decline rested, by contrast, on a single proposed causal narrative connecting that well-established physical event to several separately documented biological and cultural phenomena, without the same kind of multiple, independently converging lines of direct evidence supporting the causal connection itself, rather than merely the underlying physical event. Both explanations agreed had genuinely occurred. Panovska's analysis found that average beryllium-10 production during the Laschamps excursion ran at roughly twice the modern rate, confirming a substantial, sustained increase in cosmic radiation reaching the upper atmosphere throughout the event. Combining this cosmogenic evidence with the direct paleomagnetic field reconstructions, her work established a considerably more precise chronology than had previously been available. The full excursion, from initial onset to eventual recovery, back to something resembling stable field behavior, spanned approximately 2,000 years. Within that broader window, however, the most severe changes, the sharpest reduction in dipole field strength, and the most dramatic tilting of the magnetic axis away from its usual alignment with Earth's rotational axis, were concentrated into a considerably shorter, more intense window of roughly 300 years. The period during which the field's polarity was genuinely, measurably reversed, rather than simply weakened or in transition, lasted approximately 440 years. This refined timeline matters considerably for understanding the true character of the event, because it clarifies that the Laschamps excursion was not a single uniform 2,000-year-long period of weakened field strength, but rather a longer window of gradual field degradation, bracketing a much sharper, much more violent core episode. A genuine, brief planetary crisis compressed into a period shorter than the span of recorded human history, nested within a considerably longer period of gradual onset and gradual recovery on either side. During that sharpest, most severe 300-year window, field strength reduction reached, by the most detailed current reconstructions, levels as low as 6% of the field's modern intensity. A reduction so severe that the field's usual simple dipole structure, the familiar bar magnet-like configuration that produces the two clearly defined magnetic poles we rely on for compass navigation today, effectively broke down entirely. In its place, researchers reconstructing this period describe a considerably more chaotic, multipolar field structure, with multiple weaker regional magnetic poles scattered across the globe, rather than the two clean, dominant poles the field maintains under normal, stable conditions. A structural transformation researchers have specifically compared to the considerably more complex, multipolar magnetic field structures observed today around some of the outer planets of our solar system, whose magnetic fields never developed the simple, stable dipole geometry Earth's field maintains for the overwhelming majority of its history. The comparison researchers have drawn between the Laschamps excursion's chaotic, multipolar field structure and the magnetic fields observed today around the solar system's outer planets is worth developing in more detail, because it offers a genuinely useful, physically grounded way to visualize just how unfamiliar Earth's magnetic field became during this period. Earth's magnetic field, under normal conditions, is what physicists call a dipole field, closely approximated by the simple magnetic field a bar magnet would produce, with field lines emerging from one pole, arcing around the planet and converging at the opposite pole, producing exactly the two clearly defined magnetic poles that compass navigation has relied upon for centuries. Jupiter and Saturn, the solar system's two largest planets, also maintain reasonably well-organized dipole fields generated by their own internal dynamo processes, operating within layers of electrically conductive material deep in their interiors. Uranus and Neptune, by contrast, exhibit dramatically different, considerably more chaotic magnetic field structures. First characterized in detail by NASA's Voyager 2 spacecraft during its flybys of both planets in 1986 and 1989 respectively. Rather than a simple dipole aligned reasonably close to each planet's rotational axis, Uranus and Neptune's magnetic fields are significantly offset from their respective planets' centers, tilted at steep, unusual angles relative to their rotational axes, and carry a considerably stronger multipolar component, meaning the field cannot be adequately described by a simple two-pole model at all, and instead requires a more complex mathematical description, incorporating multiple additional magnetic pole-like features scattered across the planet. The leading explanation for why Uranus and Neptune exhibit this unusual field structure, while Earth, Jupiter and Saturn maintain comparatively simple dipole fields, involves the specific internal structure of their dynamo-generating layers. Rather than a large, uniform layer of convecting conductive fluid extending through a substantial fraction of the planet's interior, as is believed to be the case for Earth's outer core, current models suggest Uranus and Neptune's magnetic fields may be generated within a comparatively thin, shell-like layer of electrically conductive fluid, likely a superionic form of water, ammonia, and methane under the planet's extreme internal pressures, positioned at an intermediate depth within the planet, rather than occupying a large, uniform core region. This thinner, shell-like dynamo geometry, current research suggests, is inherently less capable of organizing itself into the simple, stable dipole configuration. A thicker, more uniformly convecting layer like Earth's outer core typically maintains. When researchers describe Earth's magnetic field during the peak of the Laschamps excursion as resembling the multipolar structure of Uranus or Neptune, they are drawing a genuinely precise physical analogy, not simply an evocative figure of speech. For that brief, roughly 300-year window, Earth's dynamo, despite still being generated within the same large, thick outer core layer that normally produces a stable dipole, was operating in a sufficiently disrupted, unstable state that its output temporarily resembled the permanently more chaotic field structure these outer ice giants maintain as their ordinary, everyday condition. A striking reminder that Earth's usual stable dipole field is not an inevitable, guaranteed outcome of having a working internal dynamo at all, but rather a specific, comparatively well-organized state that the geodynamo maintains most of the time, and that can, under the right destabilizing conditions, temporarily break down into something considerably stranger. This structural collapse had direct, measurable consequences for the shape and behavior of Earth's protective magnetosphere, and understanding those consequences in specific physical detail is the subject of the most recent and most technically sophisticated research this film draws upon. In April of 2025, a research team led by Mukhopadhyay, working alongside Panovska and several additional collaborators, published the first detailed space plasma physics reconstruction of the excursion's effects on Earth's broader geospace environment, appearing in the journal Science Advances. Rather than focusing solely on the magnetic field's behavior at the planet's surface, this study modeled how the entire chain of connected physical systems, the geomagnetic field itself, the magnetosphere it generates, and the upper atmosphere that magnetosphere protects, responded in sequence to the dramatic field weakening and structural breakdown already established by Panovska's earlier reconstruction. The results painted a genuinely striking picture of a planet's protective systems under severe, sustained stress. As the dipole field weakened and fragmented into its multipolar configuration, the magnetosphere itself, which under normal conditions extends many tens of thousands of kilometers into space on the side facing the Sun, contracted dramatically, losing much of the protective standoff distance that normally keeps the bulk of incoming solar particles from ever reaching the upper atmosphere at all. With the magnetosphere's protective boundary pulled in dramatically closer to the planet's surface, the auroral ovals, the ring-shaped regions where charged particles are typically funneled down into the upper atmosphere near the magnetic poles, producing the visible aurora borealis and aurora australis familiar today at high latitudes, expanded dramatically and wandered far from their normal polar locations, migrating towards significantly lower latitudes than aurora displays, reach under stable modern conditions. This finding directly answers, with a level of physical specificity the original 2021 paper never attempted, one of the more genuinely striking questions this kind of research invites. What would this event actually have looked like to anyone alive on Earth's surface at the time? According to Mukhopadhyay's team's reconstruction, auroral displays during the excursion's most severe phase would very plausibly have been visible across a considerably broader swath of the planet than modern aurora activity ever reaches, potentially extending toward latitudes closer to the equator than the aurora borealis or aurora australis manage even during the most intense modern geomagnetic storms. It is worth considering, briefly and carefully, what this dramatic auroral displacement would actually have meant for the Paleolithic humans and Neanderthals living through the excursion's most severe phase, since this specific question sits at the more speculative but genuinely interesting edge of what current research can responsibly address. Aurora displays occur when charged particles funneled down along magnetic field lines into the upper atmosphere, collide with atmospheric gas molecules, and cause them to emit light. The same basic physical process, differently arranged, that produces the glow inside a neon sign. Under modern, stable field conditions, this process is confined almost entirely to a narrow ring around each magnetic pole, meaning aurora displays are, for the overwhelming majority of the global population, an exceptionally rare sight, visible with any regularity only to people living at high latitudes in Scandinavia, Alaska, northern Canada, and comparable regions near the poles. According to Mukhopadhyay's team's reconstruction, the dramatically expanded and displaced auroral ovals during Laschamps' peak would have brought this normally polar-exclusive phenomenon within potential viewing range of a considerably larger fraction of the excursion-era global population, including populations living across much of Europe, where both Neanderthals and early modern humans were present during this exact period. period. Consider, too, what this specific chronology implies about the broader relationship between this film's two central storylines: the collapsed magnetic field itself and the population of Neanderthals living through the same general period. Even setting aside the specific, now rejected causal claim that the excursion drove Neanderthal extinction, the two populations of hominins alive in Europe during this window, Neanderthals in their final centuries and anatomically modern humans in their earliest, were both independent of any dispute over causation, living through the same objectively unusual physical environment: elevated cosmic ray exposure, a structurally chaotic magnetic field, and quite possibly, per Mukhopadhyay's reconstruction, an unusually active and unusually widespread sky. Whatever ultimately explains Neanderthal disappearance, and current evidence points overwhelmingly toward competition, demographic pressure, and climate rather than any single environmental trigger tied to the magnetic field, both populations were nonetheless present for and would have directly experienced the same genuinely extraordinary planetary event this film has spent its runtime carefully reconstructing. This detail connects, at least as a genuinely reasonable speculative possibility rather than an established finding, to the broader question of Upper Paleolithic art and symbolic behavior already touched on earlier in this film. In the context of the original, since complicated Adams event claims about ochre use. Regardless of whether the specific causal link to sun protection proposed in 2021 holds up, it remains a reasonable, if currently unproven, possibility that unusually frequent, unusually widespread, and genuinely spectacular aurora displays, visible across regions where such displays would ordinarily be essentially unknown, could plausibly have represented a genuinely striking, memorable, and potentially culturally significant environmental phenomenon for the human and Neanderthal populations who witnessed them, whatever specific cultural or behavioral response, if any, those displays might have provoked. This remains, it is worth emphasizing directly, speculation rather than established finding. No direct archaeological evidence currently confirms any specific behavioral response to auroral activity during this period, and this film bars the possibility only as a genuinely interesting open question. The more precise 2025 physical reconstruction newly makes possible to ask with real scientific grounding, not as a claim equivalent in evidentiary weight to the carefully dated physical reconstructions already discussed at length. What can be said with somewhat greater confidence is that the sky itself, during the excursion's most severe centuries, would have looked measurably, visibly different across a considerably broader portion of the inhabited world than it does today, or than it did before the excursion began. A genuinely rare instance in which a deep-time geophysical event, ordinarily accessible only through careful laboratory analysis of ancient rock and ice, may have produced an effect directly, visually observable to the ordinary people living through it, without requiring any instrument more sophisticated than a clear night and a functioning pair of eyes. The broader significance of this specific 2025 study lies less in any single dramatic visual detail and more in what it represents methodologically. The first attempt to model this ancient event as a complete, physically connected system, tracing cause and effect systematically from the geodynamo deep in Earth's core, through the resulting magnetic field structure, through the magnetosphere that field generates, and finally through to the upper atmosphere's actual physical response. A considerably more rigorous and technically demanding approach than simply asserting. As the 2021 Adams event paper had, that increased surface radiation must have produced a specific list of biological and cultural consequences. Without modeling the intervening physical chain connecting cause to effect in comparable detail. Having established, through this more recent and more carefully constrained body of research, what the Laschamps excursion actually involved, a genuine, severe, precisely dated collapse of Earth's normal magnetic field structure, with real, measurable, physically modeled consequences for the planet's broader protective systems. It is worth addressing directly the question this kind of film inevitably raises. Could something comparable happen again? And is there any evidence it might be beginning already? The specific feature of Earth's current magnetic field most frequently connected to this question is the South Atlantic Anomaly, a large region currently centered roughly over South America and stretching across the South Atlantic Ocean, where the field's intensity is measurably weaker than the global average, and where satellites and spacecraft passing through the region experience elevated exposure to charged particles as a direct, practical consequence of that locally reduced magnetic shielding. Satellite data gathered continuously by the European Space Agency's SWARM mission, a constellation of 3 dedicated magnetic field monitoring satellites launched in 2013, has documented that the South Atlantic Anomaly has been growing in size and, more recently, beginning to split into 2 distinct regional lobes of weakened field strength. A structural development that bears at least a superficial resemblance to the kind of regional field complexity that characterized the early stages of the Laschamps excursion. The SWARM satellite mission itself deserves closer examination, both because it represents the primary source of the modern magnetic field data this film has already discussed, and because its specific technical design illustrates how researchers actually gather the kind of precise, continuous magnetic field measurements that make possible the sort of careful, appropriately cautious assessment of current risk this film has already presented. Launched in November of 2013 by the European Space Agency, the SWARM mission consists of 3 nearly identical satellites, each equipped with a suite of highly sensitive magnetometers, capable of measuring both the strength and precise 3-dimensional direction of the magnetic field at each satellite's location, many times per second, as the satellites orbit the planet. 2 of the 3 satellites, designated SWARM Alpha and SWARM Charlie, fly in a closely spaced side-by-side formation at a lower orbital altitude, allowing researchers to distinguish spatial gradients in the magnetic field across short horizontal distances. The 3rd satellite, SWARM Bravo, orbits at a somewhat higher altitude, providing a complementary vantage point that helps researchers separate magnetic field contributions originating from Earth's core from separate, smaller magnetic contributions originating from the crust, the oceans, and the ionosphere, each of which produces its own distinct, identifiable magnetic signature that must be carefully modeled and subtracted before the underlying core field signal can be isolated with genuine precision. This satellite constellation approach represents a considerable technical advance over the ground-based and airborne magnetic surveys that constituted the primary data source for magnetic field monitoring throughout most of the 20th century. Ground-based magnetic observatories, while capable of extremely precise, continuous measurement at their specific fixed locations, are unevenly distributed across the globe, with far denser coverage across North America, Europe, and parts of Asia than across large stretches of ocean, polar regions, and much of the southern hemisphere. Satellites orbiting the entire planet repeatedly provide comprehensive, genuinely global coverage, allowing researchers to construct considerably more complete and more evenly resolved models of the field's current structure and behavior than ground-based data alone could ever provide, and to track subtle changes in that structure, including the specific growth and splitting behavior of the South Atlantic Anomaly already discussed, with a level of confidence and geographic completeness earlier generations of researchers simply did not have access to. Data from the SWARM mission, combined with historical ground-based observatory records extending back well over a century in some locations, and with the kind of paleomagnetic rock and sediment evidence already discussed extensively throughout this film, together allow researchers to place the field's current behavior within the broader context of its documented history, distinguishing ordinary, well-precedented fluctuation from behavior that might genuinely warrant closer concern. It is precisely this combination of continuous, high-precision modern satellite monitoring and carefully reconstructed deep-time paleomagnetic history that allowed Chris Finlay's team to reach the specifically qualified conclusion already discussed regarding the South Atlantic Anomaly, neither dismissing its ongoing evolution as scientifically uninteresting, nor overstating its significance as clear evidence of an imminent excursion, but instead placing it carefully within a broader pattern of documented magnetic field behavior extending back tens of thousands of years. Chris Finlay, a geomagnetism researcher at the Technical University of Denmark's DTU Space, led an analysis of 11 years of continuous swarm satellite observations published in October of 2025, examining this specific question directly. Does the South Atlantic Anomaly's ongoing growth and structural splitting represent an early warning sign of an impending magnetic excursion or reversal, comparable to what occurred 41,000 years ago? Finlay's team's answer, stated with genuine scientific care rather than either alarmist or dismissive certainty, was that while the anomaly does share certain structural features with the documented early stages of past geomagnetic excursions, those specific features appear to represent necessary conditions for an excursion to eventually develop, rather than sufficient conditions guaranteeing that one will. In plainer terms, the current South Atlantic Anomaly shows some of the same regional field complexity that past excursions eventually developed into something more severe. But that same starting pattern has, at various points across Earth's magnetic history also simply resolved itself back into stable, ordinary field behavior without ever escalating into a genuine excursion or reversal at all. It is worth considering, even briefly and speculatively, what a Laschamps-scale excursion would actually mean for a technologically advanced civilization. Since this specific question, while necessarily hypothetical given that no comparable event has occurred since the rise of modern technology, illuminates something important about why researchers continue monitoring the field's current behavior so closely despite the appropriately cautious conclusions already discussed. Modern satellite infrastructure represents perhaps the most directly and immediately vulnerable system. Satellites in low Earth orbit already pass through the South Atlantic Anomaly regularly, and operators of the International Space Station and numerous scientific and commercial satellites already account for measurably elevated radiation exposure and increased rates of electronic component malfunction whenever their orbits carry them through this specific region. A direct, present-day, small-scale preview of the kind of elevated radiation exposure a genuinely global magnetic field weakening would produce across the entire planet's satellite infrastructure simultaneously, rather than confined to one specific regional anomaly. A dramatic global reduction in magnetic shielding comparable to Laschamps would substantially increase this kind of radiation exposure and equipment degradation risk across the thousands of active satellites currently supporting global communications, navigation, weather monitoring, and numerous other systems modern infrastructure depends upon continuously. Beyond satellites, a severely weakened magnetosphere would also leave power grids and other large-scale electrical infrastructure considerably more exposed to geomagnetically induced currents, a phenomenon already well documented during severe modern solar storm events, even under Earth's current, comparatively strong magnetic shielding. The most frequently cited historical example, the 1989 Quebec blackout, occurred when a comparatively moderate solar storm induced sufficient additional current in Canada's power grid to trigger a cascading system failure lasting roughly 9 hours and affecting millions of people, despite Earth's magnetic field operating at essentially full modern strength throughout that entire event. A magnetic field reduced to the kind of severely weakened, structurally chaotic state documented during the Laschamps excursion's peak would be expected to provide considerably less protection against comparable solar activity, potentially amplifying the frequency and severity of exactly this kind of large-scale electrical infrastructure disruption. None of this is intended as an alarmist prediction that any such event is imminent. The careful, qualified conclusion reached by Chris Finlay's team regarding the South Atlantic Anomaly, already discussed in detail, remains the appropriately measured current scientific position. But this brief consideration of modern technological vulnerability helps explain why continuous satellite monitoring of the field's evolution, of exactly the kind the swarm mission provides, represents a genuinely valuable, actively maintained scientific and practical priority, entirely independent of whether any dramatic excursion event ever actually develops. Understanding precisely how Earth's magnetic field behaved during its last severe, well-documented collapse 41,000 years ago provides researchers with essential grounding for understanding what a comparable modern event would mean should the current South Atlantic Anomaly or some other future development in the field's behavior ever begin to escalate beyond the ordinary fluctuation the field has exhibited continuously across its entire recorded history. This is worth stating plainly because it represents exactly the kind of carefully qualified, genuinely honest scientific conclusion that rarely generates the same viral media attention the original 2021 Adams Event paper received. There is no current reliable evidence that Earth's magnetic field is beginning a new Laschamp scale collapse. The South Atlantic Anomaly is a real, measurable, actively monitored phenomenon, and it is genuinely useful and important that satellite missions like SWARM continue tracking its evolution closely, precisely because doing so is the only way researchers will be able to distinguish with genuine confidence between ordinary regional field fluctuation and the early stages of a genuine future excursion, should one ever begin to develop. But as of the most current data available, the honest answer is considerably less dramatic than either the original 2021 headlines or a hypothetical modern equivalent might prefer. Watch, measure, and wait. Because the necessary conditions being present is not the same thing as the outcome being determined. It is worth adding one final piece of context regarding how researchers currently understand the broader recurrence pattern of events like Laschamps, because it bears directly on how concerned any given generation should reasonably be about experiencing a comparable event within their own lifetime. Current estimates, drawn from the broader catalogue of documented excursions already discussed earlier in this film, suggest geomagnetic excursions of some meaningful severity occur, on average, every few tens of thousands of years, though with enough irregularity in the actual historical spacing between documented events that treating this average as a reliable predictive interval would be a significant overstatement of what the underlying data can actually support. 41,000 years have now passed since Laschamps, a span of time comparable to, though not definitively exceeding, the rough intervals separating some other documented excursions in the broader catalogue. This does not mean another excursion is overdue in any statistically rigorous sense. Geomagnetic excursions do not appear to follow a strict clock-like periodicity the way some other geophysical phenomena do, and Chris Finlay's team's carefully hedged assessment of the South Atlantic Anomaly, already discussed at length, remains the most current, most defensible position available. But it does mean that continued careful monitoring of the field's ongoing behavior remains a genuinely reasonable long-term scientific priority, precisely because the honest answer to when the next such event might occur remains, and will likely remain for the foreseeable future, that researchers simply do not yet know. What this entire investigation ultimately traces, from the volcanic rocks first sampled near a small French village in the 1960s, through a global media sensation in 2021, through a careful, methodical scientific rebuttal, through an increasingly precise physical reconstruction across 2024 and 2025, and finally to an honest, appropriately uncertain assessment of present-day risk, is not really a story about Neanderthals, or about ozone depletion, or about any of the specific dramatic biological consequences the Adams event paper originally proposed. It is a story about how a genuinely extraordinary physical event in Earth's deep history, a planet's protective magnetic shield collapsing to a fraction of its normal strength, its auroras wandering toward the equator, its cosmic ray exposure doubling, required years of careful, incremental, occasionally adversarial scientific work to be understood accurately, stripped of an attractive but ultimately unsupported causal narrative and rebuilt instead on a foundation of precisely dated, physically modeled, genuinely verified evidence. There is a broader pattern worth drawing out from this entire investigation, one that extends well beyond the specific physics of Earth's magnetic field and touches on something closer to the actual texture of how scientific understanding genuinely progresses, as opposed to how it is often popularly imagined to progress. The 2021 Adams event paper was not bad science in the sense of fabricated data or deliberately misleading analysis. The underlying Kauri tree record was genuine, carefully collected, and rigorously analyzed. The broader paleomagnetic and cosmogenic radionuclide evidence establishing that Earth's field genuinely, dramatically weakened 41,000 years ago was never seriously disputed by any subsequent researcher. What made the paper's broader public reception genuinely misleading was not the core physical measurement, but the speculative causal architecture built rapidly on top of that measurement, and then communicated to the public with a level of narrative confidence. The underlying evidence did not yet fully support, a pattern this film has now traced in comparable form across several entirely different scientific contexts, suggesting it reflects something closer to a structural feature of how dramatic scientific findings move from specialist journals into global public awareness, rather than a unique failure specific to this one research team or this one finding. It is worth being precise about one further methodological point, because it illustrates just how much analytical sophistication now stands behind seemingly simple statements like, "The field weakened to 6% of its modern strength." Reconstructing a single global paleo-intensity value for a specific moment 41,000 years ago requires combining hundreds of individual rock and sediment measurements, gathered from dozens of sites scattered unevenly across the planet, each carrying its own independent dating uncertainty, its own local geological complications, and its own specific limitations regarding how precisely and how completely it preserved the ambient field at the moment of its formation. Panovska's 2024 reconstruction, and the broader modeling effort building on it, relies on Bayesian statistical methods specifically designed to weigh and combine this genuinely messy, geographically unevenly dated body of evidence into a single, coherent, probabilistically weighted global reconstruction, rather than simply averaging measurements together in a cruder way that would risk being dominated by whichever regions happen to have the most abundant surviving rock record, rather than genuinely representing the planet's global magnetic behavior as a whole. None of this technical complexity is intended to suggest that earlier, less sophisticated analyses were worthless, or that the field will never again produce a headline-grabbing claim that later requires careful correction. It is intended, instead, to illustrate what genuinely rigorous reconstruction of a deep-time physical event actually requires, and why the version of the Laschamps story available today, 5 years after the Adams event first made global headlines, is grounded in a considerably more solid, more thoroughly cross-checked evidentiary foundation than the version that first captured public attention in 2021. Not because the original researchers were careless, but because 5 additional years of dedicated, unglamorous, methodologically careful work by multiple independent research groups have simply had time to happen since. The correction process that followed is in its own way the more genuinely instructive part of this entire story. Picin and Hawks's rebuttal did not require new data, new fieldwork, or new technology. It required, essentially, the patient, unglamorous work of laying 2 already existing, independently established timelines: the magnetic field reconstruction and the Neanderthal archaeological record, directly alongside one another and checking carefully whether they actually lined up the way the original paper's narrative required. This is exactly the kind of work that rarely generates headlines of its own, precisely because a rebuttal paper announcing the dates do not match as closely as previously claimed lacks the immediate narrative punch of the original dramatic announcement it corrects, even when the rebuttal represents the more careful, more rigorous piece of scientific work. What followed the rebuttal across 2024 and 2025 represents scientific progress operating at its most genuinely productive, not simply tearing down an overreaching claim and stopping there, but methodically rebuilding a more precise, more physically grounded understanding of what the underlying event actually involved. Panovska's refined chronology, Mukhopadhyay's space plasma reconstruction, Finlay's careful, appropriately hedged assessment of present-day risk. None of these later contributions generated anything close to the media attention the original 2021 paper received, despite representing, collectively, a considerably more sophisticated and more reliable body of knowledge about this ancient event than the paper that first brought it to global public attention. It is also worth situating this entire investigation within the broader arc of the 20th and 21st century's growing capacity to reconstruct deep-time planetary events with genuine physical precision. Norbert Bonhomme and Jacques Babkin, working in the 1960s with the analytical tools available to them at the time, could identify that something anomalous had occurred at Laschamps, but had no realistic means of reconstructing the event's global scope, its precise duration, its effect on the magnetosphere, or its visual consequences for anyone alive to witness it. Each subsequent generation of researchers, equipped with progressively more sensitive instruments, larger comparative data sets, and more sophisticated computational modeling capability, has been able to extract measurably more detail from the same underlying physical evidence, the same ancient rock, the same ice cores, the same basic category of cosmogenic isotope. This trajectory, from a single puzzling anomaly in French volcanic rock to a fully modeled, physically connected reconstruction spanning the core, the magnetosphere, and the upper atmosphere, represents genuine scientific progress in the fullest sense. entirely independent of the specific rise and fall of the Adams event's more speculative biological claims. This is worth sitting with directly, because it suggests something important about how any person encountering dramatic scientific claims in ordinary life might reasonably calibrate their own confidence. The initial, most attention-grabbing version of a scientific story is not necessarily the most accurate version, and it is very often not the final version. The version that survives sustained scrutiny across multiple independent research groups. Refined patiently across several subsequent years by researchers working through the genuinely difficult, unglamorous task of checking whether the exciting version actually holds up under close examination, tends to look considerably different from and considerably more modest than the version that first made headlines. Not because science is untrustworthy, but because trustworthy science is, definitionally, the version that has already survived exactly this kind of sustained, adversarial, patient correction process, rather than the version still awaiting it.